So thanks for all coming again. So let me just recap what we've done so far. So we built up theory about the Broward group, then showed how we can use it to create these abstractions. Then I said last lecture what we want is to figure out classes of varieties for which these hold, and I gave you a conjectural picture. But I said in my notes that the goal was really to be sort of a user's guide, like how do you actually compute these things? So that's the plan for the next two lectures. I'm going to try to give as many of the gory details for actually figuring these things out in a particular example. I probably can't do all of them, but I'm going to do as much as I can. So the example we're going to consider is this one we've already seen. So this will be K3 surface Y. It's a degree 8 K3. It's just a coincidence that degree 8 K3s also came up in Verily Alvarado's talk. It's just because we're doing low degree things. So So we're going to consider the intersection of three quadrics, s squared minus 5t squared. This is x squared plus 3xy plus 2y squared, and u squared equals 12x squared plus 111 y squared plus 13z squared. Okay, so this is our K3 surface. So Verily Alvarado said in his first lecture when he talked about geometry of K3s that any smooth complete intersection of three quadrics in P5 is a K3 surface. It's called a degree 8 K3 surface. So this is indeed smooth. You can check using the Jacobian criterion that this is smooth. So the reason why I wrote the equations in this way with this separation of variables is because this kind of separation of variables is going to allow me to give a fixed point free involution, which will then give me an Enrique surface. And that's the variety I want to study. So if you consider the involution on P5, which flips the signs of three of the variables, either the ones on this side or the ones on that side. So let's just do minus s minus t minus u, x, y, z. So if you think about what happens when you restrict this to y, well, what are the fixed points of this involution? They're either when s, t, and u are all 0, or they're when x, y, and z are all 0. So if we look what happens when you restrict that to y, say s, y, t are all 0, I just cover this up. And now I'm looking at the intersection of these three conics, and I can think of this just as in P2. And as long as my conics are generic enough, three conics in P2 will not intersect, so there will be no fixed points. And this is the side you should be more worried about because these do not look generic at all, but they're in fact enough that there's still no intersection. So sigma restricted to y has no fixed points. So by the theorem I stated yesterday, the quotient is an Enrique surface. Okay, so this is the surface that I want to study. So the reason why I want to look at it as an Enrique surface is because we have basically interesting parts of everything. We have étale covers, we have a transcendental, we have non-trivial Broward group over algebraic closure, we have interesting Picard group, so hopefully you'll get to see everything. Okay, I also want to say, so it is possible to give equations for x to projectively embed x, but to do that, you really have to give a lot of equations in some very high dimensional projective space. I think you want P11, and then you have many quadric relations plus some linear ones. So it's actually, the way we study quotients is as much as possible we reduce to considering things on the K3 surface. So we're constantly going to be moving back and forth between the K3 and the Enrique surface. And this slide will continually reappear and be modified. Okay, so what's the theorem? that I want to mention. So this is a theorem combined from two papers, one joint with Fairley Alvarado and one joint with Balistrieri, Berg, Manes, Park, myself. So for this particular Enrique surface, we have an Étal-Brouwer obstruction. Oh, I didn't say it. I'm doing this over Q. Étal-Brouwer obstruction to the Hasse principle, and the no Brouwer-Manin obstruction to the Hasse principle. Okay, so that's the goal, to prove this. So why did I put two papers? Well, in this first paper, what we showed is that the Étal-Brouwer set is empty and the algebraic Brouwer set is non-empty. And at that time, which was 2000, I think this appeared 2011, that was the best we could do because we really had very limited understanding of the transcendental Brouwer group. But it's not that long ago now. We still have made a lot of advances. So in this paper, what we showed was that these two sets are actually equal. So then combine it and get that it's non-equal. So the green is what I'm going to do today, and the blue is what I'm going to do tomorrow. Okay. So let's first start with just, computing the Étal-Brouwer set, the Brouwer group. It's kind of involved. You might as well first check that it's worth it. So let's first check that there actually are local points. Otherwise, I'm going to be kicking myself at the end. This was actually published, so I know that I'm not going to be kicking myself, but we're pretending we're doing this from scratch. Okay, so what we actually prove is not just that the X has adelic points, but that the K3 surface has adelic points. And we will see later today that even though this seems something stronger than we need, if we want to know that there's a non-empty algebraic Brouwer set, then we really do need that Y itself has no adelic points. Okay, so how do we do this? Well, as I've been saying, what we want to do is first deal with all but finitely many places. And if you just want to know, theoretically, that yes, you can get rid of all but finitely many places in one fell swoop, as has been pointed out in many of the lectures, all you need are the Lang-Weil bounds. But we want to get rid of as large of a set as possible, so we're going to use the full strength of the Weil conjectures. So the Weil conjectures, which as I said were proved by Deligne, say that if you have a smooth projective variety over FQ, that is the reduction, and now we all know how to reduce varieties, of some complex, not complex, Q-bar variety, then the number of points over FQ to the M, you can write, it's I equals 0 to 2n minus 1 to the I, and then you get the sum. Make sure I don't change my notation halfway through. So you embed Q bar into the complex numbers, you view this as a complex variety, compute the Betti numbers, and these are roots of the polynomials that appear in the expression of the exponential function as a, in the expression of the power series as a rational function. And what are these aij's? Well, we know they're algebraic integers, and their absolute value is q to the I over 2. Okay. So we're going to use that for y. So remember, y is a K3 surface. So just any m. If you take the points over any extension of FQ, you can get this formula, and it's all in terms of this alpha ij. So this is similar to what was happening in Vakil's lectures. You get some information just about V over F, well, in this case over C, kind of. but then it's telling you things about what's happening over the extensions. Okay, so for a K3 surface, we know what the Betti numbers are. So the Betti numbers are 1, 0, 22, 0, and 1. So, and also, we know if you look at the rational function, it's only the middle term that is left as unknown. So we get 1 plus the sum from j equals 1 to 22, alpha 2j plus p squared. Okay, so that's what this boils down to. And now we want to know when we definitely know this is going to be positive. So what we know about the alpha 2j's is that they have absolute value p. So the smallest they can be is minus p. So this is always going to be bigger than or equal to 1 minus 22p plus p squared. So in particular, y of fp is non-empty if p is greater than 23, and also, greater than or equal to 23, and also that I can actually apply the Weil conjecture so that y has good reduction at fp. Okay, so I don't just know I get to throw all of them out. I get to throw all of them out as long as it's bigger than or equal to 23 and has good reduction. And then Hensel's lemma says that y of qp is not empty. Okay, so now we need to figure out what is the primes of good reduction. Well, this is a nice complete intersection. So the Jacobian criterion tells us if we're over a field, the Jacobian criterion tells us that this is smooth as long as the matrix of partial derivatives has full rank. So we just write the matrix of partial derivatives. That's a 3x6 matrix. We look at the 3x3 minors, and we want these equations to be satisfied as well. And we want not the trivial solution. So that's what you can do over any given field. But of course, we want to know for each prime, is it good reduction? So the thing I just said, you can do all over Z. So you just take this ideal, do the minors, spit it out, put it into a computer. That ideal that you get will have a generator that's an integer, and the primes dividing that integer are exactly the primes of bad reduction. So yeah, maybe this is not worth working out, but you're left with, so these are the primes of bad reduction: 2, 3, 5, 13, 37, 59, 151, 157, 179, 821, 881, and 1433. That's your list, okay? And then you have to throw in the primes less than 23 as well. So, you know, it's maybe a little long, but it's finite. And you can just ask something, you can just actually ask a computer if you have QP points for a finite list of primes. So you just do that, and we're done. Computer says yes. Okay. The good thing about this is the computer program should actually spit out for you a p-adic point up to a certain precision. So you can then check for yourself that the computer is actually correct. So it's like asking a fortune teller. And then you verify whether or not the fortune is true. Okay. So now we have adelic points. So now we feel like, okay, we're not going to be wasting my time if I try to compute these obstructions. So let me just point out something. Whenever you're trying to these kind of theorems where you're showing insufficiency of some kind of obstruction, the difficulty in here is actually choosing the example. But once you choose the example, it's generally not so difficult to show that this is something, because I don't have to compute all of the elements in the Brouwer group or show you a particular one or show you how I came up with it. I just have to pull it out of the sky and show you that it obstructs it. But if you're showing something as non-empty, then you have to consider all of the possible Brouwer classes, show that you've found everything, compute the obstruction for everything. So the difficulty that goes into here is mostly hidden in all of the papers. If I have time, I will say a few words about how we actually came up with this example at the end. But this is a lot of trial and error to get something which looks very nice at the end. And then this, here you generally see the work. Okay. So now we're going to prove that there actually are no rational points. So let's recall the definition of the Étal-Brouwer set. What do? I take the intersection over all, I'll call these primes, torsors under finite Étal groups. And then for each of those, I take the union over all elements all isomorphism classes of G torsors over K. And then I look at the twist of this, take the adelic points there, take the Brouwer group there, and map it down. Okay, so for a Enrique surface, well, so it has an Étal double cover that's a K3 surface, but then K3 surfaces are simply connected. They have no non-trivial Étal any covers, not just double covers. So if X is an Enrique surface, the only non-trivial Étal cover is the K3 surface. Okay, so for the Enrique surface, this reduces to just considering the elements in H1. So it's a torsor under Z mod 2. So this is Q. This is isomorphic to Q star mod squares. So you just take a representative in here, twist our torsor, take the adelic points, take the Brouwer set, map them down. Okay. Technically, I should also include, let me do this, should also include the Brouwer set of X, but I'm actually going to show this part is empty, and also in general, you can show that this is contained inside this set. So, you know, I might as well have removed it from the beginning. But there's two alternatives to just reducing to proving this is empty. Okay. And very conveniently, in my second lecture, I told you what these y sub d's were. Right? So y sub d, and I left it as an exercise, which I'm sure all of you have done, that the twist is exactly this. Okay, so we need to look at these K3 surfaces and check that they have no adelic points. So I'm going to assume that D is a square-free integer. Yes? This one? Okay. So let me see if I can do this. Is that going to fall off the table? Is that okay? Yes? Okay. Oh, yeah, thank you. Yes, that would be an amazing theorem. Okay, so our X is proper. So I do know from the general theorem that I stated on Monday. I'm going to stop trying to say dates. First lecture, second lecture, that this just reduces to a finite union. So, but the way you show that it reduces to a finite union is it's kind of similar to considering the adelic points. The things that cause you problems are the primes of bad reduction. So I could just go through my list of primes of bad reduction. Uh-oh, very quickly. Primes of bad reduction. And then check for each of those, apply the Weil conjectures, do that. But it turns out in this nice example, because we made this example, we can just sort of case by case. It's actually quicker to just deal with all the D's at once. So that's what I'm going to do. So we'll break it into 4 cases. So one is that there exists a prime dividing my square-free integer, which is not 2 or 5. So then let's assume that we have a solution. What I'm going to show is that then there are no QP points on this twist. So let's assume that there is a solution. Okay, and let me scale it to assume that the solution is primitive. So all of the coordinates are in ZP, and at least one of them is in ZP cross. So now if we go to this K3 surface, D is square free and it's divisible by P. So if I reduce mod P, I get this. So if now I'm considering this being 0 mod P. So one obvious way to do this is that all of X, Y, and Z are 0 mod P. So let's, this is case 1A. X, Y, Z are 0 mod P. Well, then this side is 0 mod P squared. So this has to be 0 mod P squared. So that means that s squared minus 5t squared, and u squared have to be 0 mod P. And then all of them are 0 mod P and contradiction. Okay, so now we can assume that at least one of X, Y, and Z are non-zero mod P. Okay, and we're looking at the equations xy plus 5z squared congruent to 0 mod P. I'm going to rewrite it slightly differently. 12x squared plus 111y squared plus 13z squared is 0 mod P. And this factors as x plus y times x plus 2y. So either you get x plus y is 0 mod P, or x plus 2y is 0 mod P. I just have been teaching ring theory, so I have this incredible urge to say, and we're in an integral domain, so we know there's no zero divisors. Okay, so let's look at this case. Well, then x has to be congruent to minus y mod P. So if we plug these in, then we get x squared, no, minus x squared plus 5z squared, congruent to 0, and 123 x squared plus 13z squared. It's congruent to 0. So you immediately run into a contradiction if these equations are linearly independent. So this is okay, contradiction, unless, and these equations are linearly dependent when P is either 2, which we ruled out, or P is 157. But when P is 157, this is 2 mod 5. So 5 is a non-square mod P, so you have no non-trivial solution here. So then we also have a contradiction. But then 5 is not in FP star squared. So, okay. Right? And let me just say again, this is because we rigged this to happen, right? We searched and searched and searched these funny equations, 12, 1, 11, 13, to make arguments like this work. And if you take x plus 2y congruent to 0 mod p, you get a similar thing. You get an equation. It's okay as long as they're linearly independent. The case where they're linearly dependent, then something is not a square. You get a different contradiction. Okay, so that deals with almost everything. Right, now we're left with a finite list. Okay, I'm going to remove this. This is going to fall off the table. Okay. So what are the rest of the cases? Okay, I guess it's 5 cases. So one is if D is negative, then this last solution has no real solutions. So y sub D of R has no non-trivial solutions, and then you can check no non-trivial for the last means no non-trivial for everything. If D is 2 mod 3, then also this last solution has no non-trivial Q3 solutions, and trivial solutions there mean trivial solutions for everything. And the last one, so now we're down. If you go through something which is a positive integer which is only divisible by 2 or 5, and you take care of all the ones that are 2 mod 3, all you're left with is D is 10 or D is 1. So if D is 10, then we show that Y10 of Q5 is empty. And okay, I did promise almost all the gory details, but I'm just going to leave that one. Okay, so the one we're left with is D equals 1. And we're not going to be able to use just a purely local argument here, right? Because I said at the beginning, D equals 1 is just y, and we already know that y has everywhere local points. So we knew that these arguments would fail for D equals 1. So what are we going to consider? Well, notice, let's pretend that D is 1. I can project from the u coordinate, just project onto the P4, which has st, x, y, and z as the coordinates. Let's go from P5, rational map to P4. And then what is the image of that? This map S, which is just given by these first 2 equations. Okay, and also very conveniently in my earlier lecture, I told you that on this S, the element 5 x plus y over x is in the Brouwer group of S that we computed. And we saw that S of AQ of alpha is the empty set. So that implies that S of Q is the empty set. Okay, so that definitely tells you that y has no rational points, but let's explain why it also has a Brouwer-Monod obstruction. Well, so let's remember what happens with the Brouwer-Monod obstruction. What are we doing? We're taking an adelic point, and we're pulling back the Brouwer class here. But if I take this Brouwer class on S, I can pull it back to y, and then pull it back to this point. But that's the same as if I just considered this adelic point as an adelic point on S and pulled it back this way. Okay, so what this diagram shows is that if you map down the adelic points orthogonal to the pullback of alpha that's contained in the set of adelic points orthogonal to alpha on S. So this is empty, so this is empty. Okay, does that make sense? So now we've shown that the Étoile-Brouwer obstruction is empty. And again, this was rigged. That's why we took these first two equations. I think I forgot to mention this in the other lecture, but we did not develop this example. This is an example due to Birch and Swinnerton Dyer. I think I'm one of the only people in the world that cites this paper more than their paper with the conjecture. And as Coluccilen reminded me, this is the 40th year anniversary of this paper. This was in 1975. Okay, oh, this is going here. All right. So now we're going to look at the algebraic Brouwer set. Okay. Did I start at 10:10? Is that right? Somebody who's official? Yeah, okay, great. So how are we going to do this? Well, let's forget whose lecture this was set in, but from spectral sequence argument, we get that Brouwer 1 mod Brouwer 0 M over Q. So this is isomorphic to H1 of the absolute Galois group acting on pick X bar. So our first step to understanding the algebraic Brouwer set is to understand pick X bar as a Galois module. So for Enrique surfaces, our life is slightly easier than it is for K3 surfaces because pick X bar is completely understood for Enrique surfaces. So for any Enrique surface, pick X bar fits into the following exact sequence. So there's torsion. This is isomorphic to Z mod 2, generated by the canonical divisor. And then the quotient is the group of numerical equivalents, group of divisors up to numerical equivalence, which is the same as Néron-Severi. And this is isomorphic to the hyperbolic plane, direct sum, a negative copy of the E8 lattice. Okay. This is not a coincidence. It's because we have the K3 as a double cover, so there's some relation between the Picard group of the Enriques and the Picard group of the K3, so it's not a surprise that this is very similar to what you see for the K3 surface. But in particular, we don't get that this is contained in something like this. We get that it's isomorphic to something like that. So there is no question about the rank of the Picard group on an Enrique surface. So that's nice. Okay, so when I look at the long exact sequence from cohomology, what I want is here, and this maps to H1 GQ num X bar. And from here, I get an H1 GQ KX H0 num X bar. Okay, so KX, this is isomorphic to Z mod 2, so this is very big. This is a Q star mod squares. So whenever you have torsion in your Picard group, you're always going to have an infinite Brouwer group mod quotients. So this is very big, and it seems like it's going to be very difficult to deal with, but actually there's very nice theory using the descent theory laid out by Coluccilen and Sansuk, which is explained very nicely in this book of Skorobogatov, that allows us to deal with this part all at once. So even though this seems like it's going to be incredibly annoying, this one is actually easy. This part is easier to understand. So I guess I don't need the equations right now. Okay. So this proposition, as I said, is using the descent machinery, and it's a proposition in Skor-Bogatov's book, that if we take the adelic points that are orthogonal not to the whole Brouwer 1, but just to the part that we get from this infinite part coming from the kx. So you should think this two-torsion canonical class, this is the element which is giving us our étale double cover. So from a torsion class, you can create an unramified cover of degree equal to the order of the class. This is the thing that gives us our K3 surface. So this should somehow be related to what we get on the K3 surface. And in fact, this is exactly the union over all of the d's in q star by q star squared of the rational points on the twist. No Brouwer set, just mapped down. Okay, so this is why I really wanted one of the twists to have adelic points. Because if all of them failed to have adelic points, then immediately this would be coming from an algebraic Brouwer-Monod obstruction. So if I want anything new, I have to have this more somewhere. This more complicated argument that involves the Brouwer-Monod obstruction. Okay. And then we already saw that y1 of AQ is non-empty. So this whole thing is non-empty. Okay. Maybe I should explain. Okay. If I have time at the end, I'll come back and try to give more of a thing about why this is true. Probably I won't have time. But. Okay. So now we're left to consider what the co-kernel of this map is. The co-kernel from H1 of the canonical divisor to H1 of pic. So to first approximation, we can compute what is H1 of num x bar. So why do I prefer doing this than pic directly? It's because in num, all of the relations and what Galois action does, I can write in terms of, I can figure out in terms of intersection numbers. I just take generators for my Picard group, I act by Galois on the coefficients. To figure out how I write it in terms of my basis for num, I just compute intersection numbers. If I want to instead figure out what it is in the Picard group, then I actually have to find a linear equivalence in terms of the basis elements. And I mean, that's not something I want to do. If I can do it this way, I might as well do it this way. That's why I split it up. So we know what num x bar is as a group. We need to know what it is as a Galois module. So one way I can do that is that I can find curves that generate it and then do the procedure that I just outlined. I write down the equations of the curves, I act by Galois on the coefficients, sends it to something else. So I want to find curves on X. And actually, what I want to do is to find curves. Remember, I said working with the equations of X directly is very annoying. So what I'm instead going to do is find curves on Y whose classes are sigma invariant. Okay, so I instead look for classes on Y which are fixed by sigma, and then I can prove that that means that they come from X. So that's what I am going to do. So our way of looking for curves is going to follow, this is explained in Beauville's book. So a nice consequence of working with these nice types of K3 surfaces is that they've been studied classically. People have looked for curves on them. We have ways of finding curves on these K3s. Similar to, for the degree 2 K3s, finding a tritangent line to the sextic gives you an extra curve class. There are similar classical methods that work here. So what do I want to do? Well, instead of y is an intersection of 3 quadrics, so I can consider this, call it script y over P2, what's classically called a net of quadrics. So I can think of this in P5 cross P2, and say if I call this 1Q1, Q2, and Q3, I just take the family parameterized by P2. So this is lambda Q1 plus mu Q2 plus nu Q3. Okay? So I take these net of quadrics. Sounds like I'm going fishing. Okay, so I take these net of quadrics. So how are we going to get new curve classes on here? Well, what I can consider in P2 is look at the degeneracy locus of the net. So I can look at the locus in P2 where these quadrics drop rank. And how do I compute that? Well, a quadric I can think of as a symmetric matrix. I'm over Q, so I don't have to worry about characteristic 2. And the rank of the quadric is exactly the rank of the symmetric matrix. So when it drops rank, I want the determinant to be 0. So I just write each of these quadrics in terms of a symmetric matrix. I take lambda times this one plus mu times that one plus nu times that one. I get a 6 by 6 symmetric matrix with linear forms in lambda, mu, and nu, and I take its determinant. So that will give me a sextic, but there's something very nice about these equations and my sextic breaks up a lot. I get 4 lines. Oh, this is going to be a terrible drawing. Now I'm never going to be able to intersect these. 4 lines and a conic. Okay, and why did I draw 3 of the lines in green and the conic and line in red? Well, if you think about what happens to this 6 by 6 matrix, oh, thank you. So if I think about what happens when I look at this 6 by 6 matrix, so just because I have this partition of the variables, because I have the STs and U's on this side and the XY's and Z's on that side, there's no mixed terms. So this 6 by 6 matrix really naturally, come from the involution, splits up into 2 3 by 3 blocks. So I definitely have an intersection of 2 cubics. And then because I picked special equations, it breaks up even more. So the red and the green are the cubics that I get from the division, and then the lines are breaking up further. Okay, so this degeneracy locus has lots of singular points from every intersection. So a singular point of the degeneracy locus, an isolated singular point, all of these are isolated, corresponds to a rank 4 quadric. Okay, so a rank 4 quadric, that's going to be some sort of cone over a quadric surface. So I have rulings on it. And those rulings are going to give me new curves. So let me take, let QT be a rank 4 quadric. So then, from the vanishing of QT, not boldface Q, quadric Q, I get 2 maps to P1 corresponding to the 2 rulings that you have on a quadric surface. Okay, these will not necessarily be defined over the ground field. You may have to make some extension. Okay, I also may have to make some extension to even get the field of definition of the quadrics. So make some extension to be able to write down this quadric, and then to make some other extension to write down the rulings. Okay, so this is some rank 4 quadric. And then what is my y? It's the intersection of the 3 of these quadrics. So y contained in here, I'm intersecting 2 additional quadrics. This is v, q, t. And then some q and q prime. So if you think about what the fiber is of each of these maps, well, it's a rank 4 quadric, but a rank 4 quadric in P5. So instead of the fiber being a P1, it will be a P3. So each of these are a fibration of P3s. And then for Y, I'm intersecting with 2 additional quadrics. So I'm getting fibration of 2 quadrics in P3. So these are genus 1 fibrations. Okay, and so those are going to give me curves. A fiber of this will give me curves. And here you can see that I have, I have 14 singular points. So that gives me 14 pairs of fibrations. So I get 14 pairs of classes of genus 1 curves, which I'm going to denote Fi and Gi from I equals 1 up to 14. And you can check, well, if I take 1 fiber from each fibration and add them together, that corresponds to taking a hyperplane section on the quadric. So those are all equivalent to each other. So I really just need 1 GI and then all of the FIs. Okay, so those are some curves on the K3 surface. So I don't need this for what I'm going to say now, but in our paper we compute that those actually give you a full rank sublattice of the K3, similar to, and we use these rank bounding methods that Verily Alvarado has been talking about. Okay, so we need to figure out which ones are sigma invariant. So I'm just going to, this is a computation. So what we do is we write down equations for all these things. We write down all the points of intersection, we write down the quadrics, we take these fibers, and we get these very explicit generators. Can you see? Okay, A, B, and C, we actually, in our paper, this 12 is an A, this 111 is a B, and this 13 is a C, and we give different conditions for when various parts work. Okay, so we just write this down. Took a while. Actually, for a long time, we just had this handwritten on a piece of paper, and then we realized that we were really screwed if we lost that piece of paper. So don't do that if you do this. Type it up. Yeah, and then you just look at the equations, you act by Galois, and you can see, so for some of these ones, F10 and G10, so if I act by sigma on this, this will send s minus square root 5z comma x to s plus square root 5z comma x, which will be a fiber of the G10 fibration. So that curve class will not be fixed by Galois, and that's why we have no entries in this x. These curve classes do not descend to the Enrique surface. And what's the difference? The ones that descend are exactly the ones that you should know you get because you have an Enrique surface. They're the ones that come from the intersection of a red curve with a green curve. Those are the ones that descend. Okay, so that gives you these 9 pairs, and then we compute those. It turns out that these curves do not generate the full Picard group, they generate an index 2 subgroup, but we play around. There's only finitely many possibilities for the index 2 subgroup, and we just check. that whatever the superlattice that contains it is, its H1 is trivial. So H1 of num x bar is 0. We don't exactly have generators for it, but whatever the generators are, we know enough information that we can compute that this is 0. So then, yeah. So that means that this part coming from this image of H1 is actually somewhere. Yeah, it's the whole algebraic Brauer group, because this goes away, this goes to 0, so everything comes from the image of here, and we already showed that that part is non-empty. Okay, so we get down to the messy business. All right, so that's it for today.